Hello students, today I discuss about adiabatic change. So its definition is that if no heat can be allowed to outside of a system of gas or inside of it at the time of its change, means the change of the system of gas in pressure and volume. The change is called adiabatic change. Means if no heat can be allowed to outside of a system of gas when it is being changed in pressure or volume, then this change is called adiabatic change. So this is the definition of adiabatic change. In this change, actually the amount of heat is equal to 0 because no heat can be allowed to the outside or of the system of the gas or inside of it. So the amount of heat in this change is equal to 0. So from the first law of thermodynamics we will get Q is equal to change of internal energy plus work done in this change. So here Q is equal to 0, change of heat. So we will get change of internal energy is equal to minus W. Means if work is done, then internal energy is will be decreased because for work done all the heat actually all the internal energy is used to done the work. So there will be a decrease in internal energy. So here U2 less than U1. So here due to the change in pressure or volume by external work decreases its internal energy. So what will be the work done to change its pressure or volume? The internal energy will be decreased in adiabatic expansion. Similarly, in adiabatic densing, means when the when the pressure and volume will be changed, so work done will increase the internal energy, means U2 greater than U1. So if the pressure and volume are P and V of any type during the change, we can write down in adiabatic expansion P multiply V to the power gamma is equal to constant. So this is the equation of Boyle's law in case of adiabatic change. So actually we know Boyle's law, PV is equal to constant. So here in adiabatic change it is rewritten in this way: PV P multiply V to the power gamma is equal to constant. Here gamma is equal to the ratio of specific heat at constant pressure by specific heat at constant volume. So Cp by Cv. So this is gamma. Now what is work done? If for n mole of ideal gas, the initial temperature, volume and pressure are T1, V1, P1 respectively, and after the change these is T2, V2 and P2 respectively. If we take this, then we can write down from ideal gas equation P1 V1 is equal to nRT1 and P2 V2 is equal to nRT2. So also we know that P multiply V to the power gamma is equal to constant. We will take K, say. So in this way it can be written down P1 V1 to the power gamma is equal to P2 V2 to the power gamma is equal to Pn here to the power gamma and for defined number of gas taken in a system. So work done, we can write down work done is the change in volume integration from V1 to V2 of P P dV. So integration of P under V1 to V2 with respect to dV. So here P we will get K V to the power gamma. From this P is equal to K by V to the power gamma. If we put this, we can write down K integration V1 to V2 1 by V to the power gamma dV. So if we integrate this, we will get K V to the power minus gamma plus 1 by 1 minus gamma V1 to V2. So this can be written down K 1 minus gamma V2 1 to the power gamma minus V1 1 minus gamma. So we will get here, if we take K into this bracket, we will get 1 minus 1 by gamma 1 minus gamma K V2 1 minus gamma minus K V1 1 minus gamma. So in this way we can write down 1 minus 1 minus gamma 1 by 1 minus gamma. If we put K's value P1 V1 gamma P2 V2 gamma, then we will get K is equal to P2 V2 gamma V2 1 minus gamma P1 V1 gamma V1 1 minus gamma. So we will get 1 by 1 minus gamma is equal to P2 V2. If we cancel or add to the indices P2 V2 minus P1 V1. So this is the actually work done, equation of the work done, 1 by 1 minus gamma P2 V2 minus P1 V1. So we know from the definition of adiabatic expansion that interchange of internal energy is equal to negative of work done. So if we put this work done value, we will get positive of 1 minus 1 gamma. If we change this, this will get this will be negative, and here it will be positive. So you can write out P1 V1 minus P2 V2. So it can be written down 1 by 1 minus gamma. We know we have taken P1 V1 nRT1 and P2 V2 nRT2. So we can write down here P1 V1 is equal to nRT1 minus P2 V2 nRT2. So if we take common nR 1 minus gamma, so in bracket we will get T1 minus T2. So this is the equation 1 we have written down. Now we will try to find out the relation between R and gamma. Here we know that from the specific heat relations at constant pressure and at constant volume, that Cp by Cv is equal to gamma and Cp minus Cv is equal to R. This is the ideal gas constant. So here if we replace if we divide this equation by Cv, we will get Cp by Cv minus 1 equal to R by Cv. So we will get Cp by Cv, I have taken, I have already said it is equal to gamma. So this will be gamma minus 1 is equal to R by Cv. So we can rewritten this 1 minus gamma is equal to minus R by Cv. So Cv can be written down minus R by 1 minus gamma. So here we will get Cv through R and gamma. Cv is equal to minus R by 1 minus gamma. So from by equation 1, in equation 1 if we put R in place of R by 1 minus gamma, we will get change of internal energy equal to minus N minus R 1 minus gamma T1 minus T2. This is equal to Cv. So we will get minus N Cv T1 minus T2 and Cv. So if we take negative sign in the bracket, we will get N Cv T2 minus T1. So this is the change of internal energy equal to change of internal energy during adiabatic expansion is equal to NCV T2 minus T1. Here Cv is the specific at constant volume. So this is the change of internal energy. We'll like this videos, then like, share with your friends, and if you have not subscribed, then subscribe this channel.